Good afternoon, everyone. I am Sheenam, and it's a pleasure to welcome you all on behalf of eMobility Plus and First View Group to today's insightful webinar on efficient battery modeling with the surrogate models. First and foremost, we would like to extend our sincere gratitude to our partner COMSOL for their continued support in making this session possible. Before we dive into the session, I'm pleased to introduce you our esteemed speaker, Dr. Meenakshi Phutke, technical specialist at COMSOL. Dr. Meenakshi is a technical specialist at COMSOL, specializing in electrochemistry and chemical engineering. She received her bachelor degree in chemical engineering with a gold medal from KBCNM University. She received her master's degree from Sardar Vallabhbhai National Institute of Technology and her PhD from Indian Institute of Technology, Bombay. Her area of expertise is chemical reaction engineering. Now, a brief overview of today's session. Battery modeling plays a crucial role in predicting the performance and life cycle of lithium-ion batteries. However, traditional modeling methods often struggle to balance computational speed and accuracy. While detailed physics-based models, such as the Newman model, deliver high precision, they are computationally intensive. Conversely, simplified or lumped models offer faster computation but compromise on accuracy. In today's webinar, Dr. Meenakshi will introduce surrogate modeling, a powerful approach that bridges this gap. Surrogate models, often built using machine learning techniques like deep neural networks, enable rapid simulations while retaining a high degree of fidelity. Following the presentation, we'll host a Q&A session where Dr. Meenakshi will respond to the questions submitted via Q&A box. So feel free to drop in your questions. Also, we have poll questions that will be launched during the webinar. We encourage all attendees to participate and share their responses. Now, it's my pleasure to hand over the session to our speaker, Dr. Meenakshi. The floor is all yours.
Thank you so much, Shivnam. And let me just start this session. And let me just first share the screen so that we can kickstart our presentation on today's topic. So I hope my screen is visible to you all and my voice is also clear. So let's get started. First of all, a very warm welcome to all the participants. And thank you so much for showing this interest in today's webinar topic on efficient battery simulations with surrogate models. We, all the members of COMSOL Multiphysics team, welcome you on this session where we'll discuss a lot of different topics when it comes to battery modeling and simulations, the challenges faced here and how we can address those challenges, whether you are interested in building any model for the simulations when it comes to battery, or you are interested in training your surrogates for battery simulations to get an accurate solution, yet faster solutions. So when we start discussing about battery, so we know that typically battery simulations are multiphysics in nature. Inside batteries, electrochemical reactions are happening, the transport of ions, charges, and then heat generated due to exothermic nature of these electrochemical reactions also affect the temperature distribution, which causes the degradation in batteries. The different phenomena such as intercalation and deintercalation of lithium ion, especially for lithium ion batteries which are used in electrical vehicles. For all such cases, for all such physics to capture, one needs to have ability of a multi-physics simulations, how to get all the sets of equations required for these simulations of battery in order to capture the behavior of your battery. So such detailed physics-based simulations takes a lot of efforts and time. This is where exactly we offers multiple modeling approaches for battery modelers. So they can make use of these different types of models. And in case they still want to further reduce their time, yet they don't want to compromise on the accuracy. So in that case, they can also use the advanced battery modeling techniques based on the surrogate models. So COMSOL offers both the capabilities to only simulate battery simulations or use the surrogate model and train these model in order to get the accurate and faster solutions, which can enable a simulator or a person who is studying all this system, so they can do further rectification, optimization, design studies. They can do actual virtual prototyping, or they can also develop digital twin for their battery applications. So all such various applications can be studied with the help of COMSOL multiphysics, battery simulations, and creating surrogate models for your battery systems, which might be installed in an electric vehicle, or you might be interested in BMS, and you want to see how the surrogate model can help you manage your temperature inside your battery pack. So all such various options or such objectives can be fulfilled by these simulations offered by COMSOL multiphysics. In today's session, we'll look into all different types of models available in COMSOL, how you can make use of machine learning technologies, and how you can train your surrogate models in COMSOL multiphysics environment. So one by one, we'll look into that, what different technologies of surrogate models and functions we have available in COMSOL multiphysics, what is the workflow to adapt to such methods, how you can create the different models. We also have few examples with us, which will tell you what steps to be considered when you are interested in building surrogate models for efficient battery simulations. So before going into actual topic, I would like to launch the poll question so that I'll get to know you all of my audience, whether you are a regular user of a simulation tool, or you are evaluating simulation tool for your ongoing research project, or you are new to multiphysics simulation. Please do address this first poll question, and then we'll kickstart in our today's topic discussion. So I'll just wait for a minute so that everybody can participate in the poll. Okay. So let's start the discussion on today's topic, that is battery design and simulations. For battery designing, COMSOL offers multiple scale simulations. If you are doing a micro scale level study, such as you are developing some new chemistries of batteries, or you are testing some new electrode material. So in order to do that, if you want a high accuracy, in such cases, you can study on micro scale level with COMSOL multiphysics. However, if you want to simulate result for the cell level scale, where you have the battery and you want to study the whole battery performance, so cell level to pack level, in case you are again interested to go for a higher scale, such as a pack scale, where you want to do the thermal analysis of your battery pack, and you want to capture the behavior of battery, how the degradation might affect the battery life. So all such simulation, whether it's a micro scale, cell scale, or pack scale, all options are available. On top of that, in case you have a battery pack which is installed in electric vehicles and you want to take the approach for equivalent circuit modeling, so that scale approach is also available in COMSOL multiphysics. So no matter what your objective is for simulation, battery modeling and simulations, you can work in COMSOL and make use of different modeling types available here. So different model types available are like this, which are shown over here in this presentation. Here from left to right, when you move from heterogeneous to lump model, so your model becomes more and more approximated. Your accuracy is reducing. However, your computational cost is drastically reducing. So your computational time will reduce from the if you take the approach of lump model compared to heterogeneous model. In case of heterogeneous model, which is more sophisticated model compared to other models, Here you can actually use your geometry, like you can give a particle size distribution of your electrode, how the particles are distributed in your electrode. You can give the actual tomographic information of your electrode structure. The microstructures can be captured, how the porous structure is created inside your micro scale level. You can capture that one, and here you can do all types of studies, from fundamental studies, EIS studies, to if you want to do some parameter estimation or kinetic studies, or you are testing out some new battery chemistries, or you're mixing like different cathodic materials for your battery in case of lithium ion battery. All such applications can be dealt here with the heterogeneous types of model. And in case you don't want that much accuracy, and you want to you want simulation little faster, so what you can do, you can switch towards the heterogeneous model, where the famous Newman model approach is available. So Newman framework is there in homogeneous model, where you can take an average porosities of the various components in your battery from electrodes to separator, and hence you can do taking these average values, you can do the simulations for electrode level to cell level to pack level. In homogeneous models are particularly advised, because here you can do actually the study of, you can still actually do fundamental studies, yet you can get a good accuracy compared to homogeneous models, and much better accuracy compared to lump model. So you are not that much compromising on the accuracy, you are still getting good results. However, your computational time will be drastically reduced compared to heterogeneous models. So homogeneous models are advised for all scale, whether it's electrode scale, cell scale to pack scale. However, if you are interested in doing pack simulations, a single particle model and lump model approach is advised here, because it further simplifies the framework of modeling equations, and you get the faster solutions. In single particle model, we have again the extended single particle model in COMSOL, where you can electrode wise, you can give the mechanism what is happening. So you can still capture the accurate behavior with the single particle models. And if you want to, if you don't have any information about the components of your batteries, how, what is the thickness of the positive electrode, negative electrode, what is the composition of the active material, porosity and all, if you don't have that much information and you have bought the battery from the market, and in case you want to test that battery in your battery pack, or you are testing your battery pack, so in such cases, lump models can be useful, where just by giving the SOC versus OCV data of your battery or battery pack, you can predict the behavior of your battery and do all kinds of study, degradation studies, like capacity loss studies. You can go for thermal runaway scenario case simulations and all. In all the cases or all the model types I have discussed here, from heterogeneous to single particle model, homogeneous model to lump model, all these models can be used for doing the degradation analysis of a battery or a battery pack. You can couple these different models with the multi-physics interfaces for thermal distribution analysis, or temperature analysis in your battery. For doing thermal management of your battery pack, you can couple all these couple these various models with the heat transfer physics, and you can actually see where are the regions where you are getting hotspot generation, and where you need to maintain your temperature in order to avoid scenarios such as a thermal runaway. Or if you are interested in optimizing your design of your battery pack, or you want to adapt to such a thermal management system, where you are interested in seeing how the phase change material can help you get the constant temperature throughout your battery, or more or less uniform temperature throughout your battery structure. So all such simulations, single physics simulations to multi-physics simulations, are possible with COMSOL multi-physics. On top of that, in case you are interested in doing structural analysis, you want to see due to continuous shuttling of lithium ion, particularly in case of lithium ions, when the lithium ion shuttles between charging and discharging cycle, the intercalation and de-intercalation of these ions, how it generates the stresses inside a battery. If you want to capture the swelling in case of higher degradation, in case of gas, if your electrolyte is degrading and creating gases, how your battery can be swelled. So all such kind of, whether it's a structural analysis of your battery or a thermal analysis of battery or battery lifetime prediction, or you are interested in doing equivalent circuit modeling simulations, which is for your electric vehicle. So for all such various applications, we offer these different models which can be coupled with different physics, and you can solve your problem or any type of problem when it comes to battery modeling in COMSOL multiphysics. So all these detailed models are physics based, and it takes sometimes a very high efforts and computational cost while developing all these models. But once you have this one model created, and now you want to see in a large parameter space where you want to check your model how it works in, like, for different C rates for different drive cycles, or if you want to create the digital twin from these physics based models. So in such cases, what one need to go for a surrogate model. And now here the surrogate model will come into picture, where you can use these models created in COMSOL multiphysics and further train the surrogates in order to get a faster solution, yet accurate, to create the digital twin for your battery, which you have just studied and created the model for. So let's get into the surrogate model options and what is the workflow in COMSOL multiphysics when it comes to surrogate training of the surrogate models, what different functions are available, that we'll look into shortly. So let's get into the surrogate model. So we know that the surrogate models are the accurate and faster options towards the actual physics-based model, where these simpler yet computationally inexpensive surrogate model can be used, can be trained to capture the behavior of your system, which may be very complex in nature. However, this surrogate model will help you to create models which will capture this complex behavior of your battery. Still, you will get a faster solution and accurate solution. So this surrogate model, how you can build it in COMSOL. Let's just take an workflow tips. So how you can start building a surrogate model in COMSOL. So first, as I mentioned, you can create a full model based on any earlier model types we discussed so far, lumped model or Newman model or heterogeneous model. So you can first create the full model, then you can create a design of experiment method. We can give this design of experiment method and create a digital data table, design data tables. So once you will create a one design data table where you can give inputs, outputs. So there will be the data when the battery system is subjected for the various charging condition, discharging conditions, or in case you are changing some inputs of your input for the simulations, what will be the output when you run this full physics based model. So all that data will be captured in the design data table. Now, this design data table then will be used for the training of surrogate models. So the surrogate models will be trained on the data which is created from the simulations of full models. And then further, this data then can be used to evaluate the digital twin or apps. In case once the design data table is created and you want to train your model somewhere else, so you can export this data to third party tools. Or there can be one more way, that you have some data with you and you want to import that in COMSOL and use COMSOL to train the surrogate model. That option is also available. So you can import the data from third party here as a design data table, and then train the surrogate model in COMSOL and create digital twin. So there are multiple options where you can use COMSOL multiphysics for the surrogate modeling training, and this is the simplest workflow. Whether you are starting from the full model, creating the design data table, training the surrogate model with the COMSOL multiphysics, and creating the digital twin. All these four steps can be done in COMSOL, or you can just create a full model, create design data table, and export to third-party tool, or get the data from the third-party tool, train the surrogate model in COMSOL, and again create the digital twin. So all these multiple options are available when it comes to surrogate modeling in COMSOL. And here this option is useful in case you have some let's say you have some experimental observation, large data from the system. So you can bring in that in COMSOL multiphysics and simply use our surrogate model techniques to create the digital data teams. So we offer the platform for any of the exercise mentioned over here, and how it can help us, that will look here. So like in surrogate models, we usually create these surrogate models to create the simulation apps which will work very faster when it comes to compared to the full scale physics based model. If you change some input, you need to wait to get the output. So every time you change the input, we need to simulate the model again to get the output. So the computational time can be very high when you are doing manually. But once you create the design data table and train your surrogate model, so now you have a lookup table where the input output behavior is already captured, and you are training your model based on that data table. So it knows the system very well, and hence you can get the once the surrogate model is trained, you can get the result in the couple of seconds. So this fastness of the surrogate model is particularly useful for creating digital twin. So these digital twins can be created, or you can do one more thing, that if in case you want to check the uncertainty quantification in your modeling, so you can use the surrogate model for that purpose also, for uncertainty quantification and optimization of your battery modeling, battery simulations. So various options are available, and all these options can be used for the various applications for creating apps or digital twins, so that you will get the efficient battery modeling options in with COMSOL multiphysics. So let's take an example which we will discuss in detail in today's discussion part or today's webinar. That is battery test cycle app, which we have created with in COMSOL multiphysics environment for the in order to demonstrate our capabilities when it comes to surrogate modeling. So where we have considered full Newman model in 1D, and there we have given the test cycle in 4 segments for 0 to 10, 10 to 20, 20 to 30, and to 40. In these 4 different segments, if you change different C rates and even initial state of like if you are interested in checking the changing initial state of your battery, all these different things can be given as input, and then this model is created, and you can check that the in couple of minutes we'll check how we have created the model, and it gives like results in couple of seconds. So this is the model. This is just a glimpse of the like what we can do with COMSOL multiphysics. And let's check here. Here in this animation, you can check that just by rotating the knob, you are instantly getting the result of potential, how the cell potential is changing when you are changing different C rate in different segments. And if you are changing the initial state of charge, how it's affecting the battery behavior. So this you can see in this particular example, which is for NMC graphite battery, NMC graphite battery, which is trained with the which is based on the Newman model and trained for these 4 different segments of time, where by giving different C rates, the potential is seen, the change in potential is observed. However, one more thing such as internal resistance, because in output we have the cell potential and cell OCV at a particular time. So, but just by creating E cell minus E, by giving the C rates, so the difference between 2 potentials by C rate, you can take the internal resistance. So by simply taking 2 outputs, you can see actually various different resistance as shown over here. Like that, you can quickly create such kind of apps to get in order to study your battery system in details. So before going into what steps we have considered for creating that model which we have just seen, please do participate in second poll question, and yeah, please let us know what kind of aspect of battery modeling simulation you are working on. Do you want to use these surrogate models, like how this use of surrogate model motivates you, whether your aim is faster simulations or your aim is real time creating digital twin, or you want to just reduce your computational cost, or you want to do parameter optimization or design of experiments. So you can choose your option. This option will help you to connect back after the webinar, so that will offer you like accurate solution the problem you are looking for. So yeah, I'll just wait for 2 minutes so that you can participate in this poll question, and we'll go in details of the model I've just shown you. All right. Yeah. Let's start with this model which we have created for like battery simulation test cycle. So in this model, as I mentioned, the model is based on Newman model. So that's why here in the screenshot, you can see that we are using lithium ion Newman interface for capturing the full physics of the battery. Here you can see that we have considered all the components inside a battery, electrode structure, separator, and we have given the required parameters over here. And later on, to give the drive cycle, we have used the event interface for the different segments of the cycle, and there will be an option of giving different C rates for those different segments. So in each segment of time, there will be one particular C rate, and that we can give by giving an explicit event with the help of event interface in COMSOL multiphysics. The workflow here you can see that lithium ion interface, like lithium ion interface physics is used over here, and event interface physics is used over here. This is the full model. We have not added any surrogate model techniques so far. So first we just create this model and check whether the accuracy is still there and results are good enough. Then once the full model is set, later on, once the model is set and you have one simulation, then later on we can add this step, which you are seeing over here, which is surrogate model training. In surrogate model training, when we'll switch to a demo part, I'll also show the further options for the surrogate model training those are offered by COMSOL Multiphysics. So here you can see in the screenshot as well that in surrogate model training step, we decide what are the input variables and what are the like properties which are we want in an output. So what quantities of interest we want in output parameters can be selected over here. What inputs we want to change can be selected here. So here you can see that there, as I mentioned, there were 4 segments for 0 to 10, 10 to 20. So in each segment, what kind of current you want to draw or what kind of current you want to supply in case of charging can be given with the C rates. It can be negative, positive based on discharging, charging, like that. And you can consider that SOC is the main one of the input parameters. So initial SOC will also matter. So we can give these as a 5 input, and we can take outputs such as potential of your battery, that is E cell, and OCV of your battery you can calculate. So these are the quantities of interest for output. So we can select quantities of input, quantities of interest as output over here in the surrogate model training option here. And we can say that we need to create a design data table based on design of experiment methodology. Input is given, output is given, and we are creating the table. And what are the times we want to save the data and all those steps, you can further details can be added here. And then we can create once we click on compute, we tell the software to create the design data table, which will do few simulations in this range from -5 to 5 for different segments, and will create the design data table based on the design of experiment methods that can be used. So there are multiple methods, like options are available. Multiple activation options for training are also available in COMSOL multiphysics. So there are different surrogate model functions available in COMSOL are like deep neural network, polynomial chaos expansion network, and Gaussian process network, Gaussian process functions. Here in this particular session, we'll discuss on the deep neural network functions, but other functions which are also available such as polynomial chaos expansion and Gaussian process, those will not discuss much in detail in today's part. but you can check out these two options as well. And we do have these three different function options in COMSOL multiphysics. Deep neural network functions comes with COMSOL multiphysics software. However, for PCE and Gaussian process, one might need to buy the add-on modules such as uncertainty quantification. But only with COMSOL multiphysics and battery design module, you can use the deep neural network and train your surrogate model. So you can create the design data table, and these deep neural network then can be used to train and create surrogate models. Let's take more details about the DNN configuration, like how the DNN works. So in deep neural networks, what is most important is the layering. So you have some inputs and outputs. So when input is moving, and then your simulations, like once you have a design data table, how your output can be correlated to the input with different layers. So that can be captured with the DNN layers. So these hidden layers of DNN can be of any number. Typically, if you increase the number of DNN layer, the model becomes more and more complex, and if there is a possibility of overfitting your data. So there might be a need of educated guess to in order to know how many hidden layers you can use. Quick thumb of rule that you can start with the two layers, and then if you feel that your model surrogate model is getting trained and the fitting is under, like your model is not good enough to capture the complexity, you can further add the layers. And inside layers also there will be a number of nodes or neurons. So now these, how many neurons should be there, that for that also some like prior study, like prior knowledge of your problem you are modeling, or the like the here in typically in case of battery simulations, with the prior knowledge of what problem is typically used for with how many number of layers and nodes, you can take it as a guess value, and further with the study you can get these like you can study further and get these numbers. So we do have 2-3 different model surrogate models there. You can take that as a reference and create the number of layers, hidden layers, and give the nodes. In today's battery like problem which we are discussing here is we have taken two layers, two hidden layers, and where 25 like two layers are with the 25 nodes each. Like that you can create the different architecture for your deep neural network. So the problem specific knowledge is very important when it comes to creating this architecture for DNN, and balance is equally important. As I mentioned, if you give more number of layer, you will end up with the like overfitting of your model, and your model will not perform well outside the range of your trained data. Or in case you use very less number of layers, or even nodes are less, so your neuron connections are also less. So in that case you might not be able to capture the complex nature of your problem, and hence your data prediction will be poor. And this way there is need of a balance between the number of layers and what should be the number of nodes inside your each layer. So this architecture of DNN comes with the problem specific knowledge. You can start from the templates we have in COMSOL multiphysics, and then learn with the your loss value functions, and by tracking your loss values for validation loss or training loss, by observing those trends you can like tune in your these parameters, number of layers, number of nodes, and get like a good architecture or good surrogate for your battery simulations. Here the rule of thumb is like if there are three hidden layers, you can go like 64, 32, 16, like that. However, with your like knowledge, you could adapt to any architecture for DNN, and you can use that one. So the model we created here, when you start training your model, so one convergence type of plot as shown over here will be shown in COMSOL multiphysics software. By tracking these loss values for validation loss and training loss, you can see whether your model is working well or not. Here, in case your validation losses are increasing, still your training losses are decreasing, it means your model is performing well on the trained data. However, when it is used for the other data for the validation, it's not performing well. So it means you have a overfitting in your model. So you can go back to your model, change the architecture, reduce number of layer or node, and you can then rectify the or you can take the decision based on this convergent plot and create the architecture or fine tune your architecture. In case these both losses are not decreasing and they are increasing with time, it means you have a underfit in your model. You need to add few more layer, few more nodes, and that's how you can make a decision by observing these loss value versus epoch curves. These epochs are now like number of iterations you are doing or number of times your model is getting trained. So observing these trends between validation loss and training loss, you can see how your model is or how your DNN architecture is behaving, and you can make the changes. Objective here is that your trained data should align to your finite element model data, and hence your training losses should further reduce. And along with the training losses, because simultaneously model also look for the validation losses by the some amount of data which is not used for the training purpose, but the same data which is available in the design table, the few points can be used to cross check the whether the model is getting trained nicely or not. So based on that, you can see the training losses, validation losses, observe the train, and tune in your parameters. There are multiple loss functions available in COMSOL, such as root mean squared error or absolute mean square error. So like that, different, sorry, absolute error square, like the absolute mean errors, all these different options are available. Again, different activation functions are also available to track these. So the activation functions we have in COMSOL are linear, ELU, sigmoid, and tanh. So you can use any of the activation function based on the type of like problem you are working on, and you can create the surrogate model. So now the steps with which you can handle the DNN, as I showed here, you can create first model, then design an architecture with the DNN, and then train that model to see the results. However, particularly in case of battery, the problem we are discussing here is for the test cycle. And in case of test cycle, where your things are changing with in one segment things are constant, but they can change instantly, like the discontinuity in the nature. Like here you can see that the stepwise nature of your problem. In order to capture this discontinuity with DNN network, if you go ahead with the conventional approach, the DNN model might not converge faster, or it can oscillate, or the stiffness cannot be captured completely. So to particularly capture this kind of problem, where the nature of the problem is different in different section, where in some of the part your behavior is very faster, and in so other time interval the behavior is very slow. So in order to capture this both type of transient and instantaneous behavior, which is typically observed in battery, so such kind of techniques are required, and we have used this one technique which is called as time series teaching to capture this kind of discontinuity in order to train the model with DNN techniques. So in the techniques I just mentioned, that is time series teaching. So what we do here is that we have a different time segment in which we are giving different C rates. So now the states can be different in batteries, because once we switch the like from charging to discharging, so in battery it can initially it can instantly react to that one, and later on it slowly react to that one. So this instantaneous and transient behavior which you are seeing here, so in order to capture that, if we use single DNN function, it might oscillate like this. As I told you, here you can see that in this segment, the model is right, but however, in this part, it starts oscillating. In order to avoid this one and effectively train your surrogate model, so this time series teaching, what we can do, we can divide the time segment in 4 parts. Like here in 10 seconds, we can divide the model in 10 seconds. So first what we can do is we can train our data for the one of the segment. Let's take here in case of last segment, if we keep 000C and give one initial C rate and the train the data in this segment, and later the similar train, because the model is trained for that SOC, and also we have given the window from -5 to 5C. So we have whole spectrum of C rates, whether it's a discharge or charge. So we have trained our model for both the condition discharge and charge with that particular SOC node. So what we need to do is we need to just adjust these segments on the different time scale and then stitch it together to get the results predicted from the Newman model. Here you can see these black dashed lines are the results predicted from the full Newman model. And here you can see the different segments of the different time interval, like green over here, it is stitched till this point, and later on we have stitched the red segment over here. Once the the oscillations are starting, so here we are taking the different interval and different segment is stitched back here. So like that, we can just train our model in one of the segments, in the it's preferably last segment, and then shift the model according to its C rate. It will be automatically be provided Z rate, it will automatically behave whether discharge or charge like curve is required. Based on that, you can just shift your segment and get the trends like this, and you can stitch whole segment to get the full cycle like this. In detail, here you can see that first step to model is that we take segment which is last segment 30 to 40. We take that segment of 10 seconds and we say that initially there is no C rate, and instantly we have one CSOC not initial state of charge, and we are giving one C rate in this segment. So 0 minus 5 is here. Here we'll strain for -5 to 5, and one SOC is given, and you can get trend like this. This blue here you can see. And now what we'll do is we will shift these segments back in time by creating T plus 30. And once the segment is shifted back, now you can see the same blue line is shifted back here, and it is following the dash line given by the Newman model. Like this, once the model is trained between minus C rate to plus C rate, and with that particular SOC, initial SOC, you can use the same behavior and give the different SOCs in different segments and get the behavior from your test cycle. Here the final is -5. Here we are keeping it as a rest 0 and then we are charging with 5. That behavior is captured. So discharge with -5, then rest for 20 seconds and charge with 5. See here you can see that behavior captured by stitching the time series. So like, and then you can create the algebraic function in order to like shift your data in that. So here we just train data in 30 to 40, and then we shifted it back here for this segment, initial segment, and accordingly we have given the C rate. So initially it was 0 C and then 5, and then we shift back it here, and then once we come forward, then we adjust it like -5 0 0 5 like that. So like this we can write an algebraic function and give it for the surrogate model training. So this is the time stitching series technique which can be used for a discontinuous like operations. And if you want to model the use the DNN functions to create the surrogate models for such kind of discontinuous problem. And one such complicated problem is simulated and demonstrated very well in COMSOL multiphysics. And this is details of this. So here what we are the advantages we are getting by using the method of time stitching series is that because we are only training our model in one segment, and so no need to train your model again and again in different segments. So we are saving on the time or training time. However, the other things or limitations are such that your scale or the time, like the segment for which you are using, it should be like uniform segment should be there in your test cycles, or else at least there should be a multiple of the uniform segment like that. Here in case of this particular case where the middle section was for 20 seconds, but in case we can split it in 10 seconds and we can change it like this. So there should be uniform time segment in order to create such kind of time cycle or drive cycle testing for battery. And the time segment, the smallest time segment is very important. Or here in case now it's a uniform, so you have to make sure that if it's a like multiple of your segments, the smallest segment you need to consider in order to train the data. So again, based on lot of DNN architecture, you can train this, and there are few limitation as I mentioned. Again, there are few benefits also that you are doing the training only once, so you are saving on your training time. So like this, the different techniques for creating surrogate models can be opted or adopted in COMSOL multiphysics, and you can tackle any battery simulation problem, and you can create the different surrogate models for your battery simulations. So this was the example for that one. Let's go to software and actually see the example we just discussed. Just give me a couple of minutes. Yeah, this is how when you launch the COMSOL multiphysics software, you'll end up with this interface where we have multiple options over here. But now I would like to show you the model just we have discussed here. So let's go to that model. So with COMSOL software itself, you get the application libraries. And in application libraries, the model we have just discussed is there. On top of that, other surrogate model for the battery rate capability is also available. Then for how to create a digital twin simulator or digital twin analyzer, all these different options like models are here in application library. You can check out all these models. They are very interesting models for battery simulators. And let's go into details of this particular case of lithium ion test cycle surrogate, which we have discussed in this today's session. Let's open this model and let's get into various options. Those are available for modeling the surrogate model with COMSOL multiphysics. So here you can see that, as I mentioned, that we are using NMC model, like NMC lithium ion battery. 1D model is considered. Newman approach, we are considering the for that, the physics setup you can see over here. So normally when you simulate any problem in COMSOL material, these are the general steps that you take for creating a model. That once the interface is selected, you can opt for the different materials. You can make use of material library of COMSOL, where different anodic, cathodic material and their relevant parameter properties variables are already defined. So you don't have to put a lot of efforts for creating battery models in COMSOL multiphysics. All the standard for all the standard chemistry, we do have material library, dedicated material library, which is updated every time according to the market research, like market, whatever the batteries we have in market, we update our library according to that. So we have a lot of materials for battery simulations, which you can make use of in order to create a model in few steps in COMSOL multiphysics. And once you can choose the type of model. Here the Newman model is choose here, which is lithium ion battery model, where you can say that by giving this state of charge and your battery capacity, you can give the what is your negative electrode, positive electrode. You can consider intercalation effects. You can consider the kinetics of your battery reaction, electrochemical reaction. And in order to apply the drive cycle, you can use the event function. So here you can see that the event function is used to create this IF variable, where you can give the mode of charge and discharge. In this particular case, as I said, that we have created it for 4 segments from 0 to 10, 10 to 20, 20 to 30 to 40, in which the different C rates can be given. Here you can see that we have given the different C rate for charging, discharging. That will give when we sweep the charge from -5 to 5, automatically charge or discharge both can be considered in the same one. Once the events created model is created, what we can do is after the time dependent study, when you right click, you get the option of surrogate model training. Now that option is already selected here. Here you can see that that option is added here and surrogate model training options. Now here you have two options. Either you can build table and train over here, or you can just create a design data table. Because as I mentioned during the presentation, you have both the options, just creating data table and exporting it, or creating data table and then training it on spot, or creating data table somewhere else and then training it in the same model in the different options available. So multiple options you can choose from here that train the surrogate model, the different functions we discussed, DNN, list, GP, PC, or you can see over here. Here we have just selected the option of creating data table, that with the help of design of experiment method. and the inputs are chosen, outputs are chosen over here, and we are creating the design data tables. Once the design data table is created, now you can go and train your surrogate model, which you can do over here. In global definitions, when you right click, we can see that the functions are available such as DNN, PC, GP. You can check the DNN option here, or appropriate function option which you want to take, you can take it. For this particular case, DNN option was chosen, and then we now will decide about the architecture of DNN. So in here, input and output layer will be there. In addition to that, as I mentioned, we have added two hidden layers, and two hidden layer configuration is given here, that for two hidden layers, we are again using 2525 as neurons. And the activation functions of options you can browse over from here. These different 5 activation functions are available in COMSOL, which you can use to train your model. And once the activation function is chosen, you can train and validate your model based on different optimization or advanced optimization techniques such as ADAMS or SGD. This stochastic gradient descent method, or this adaptive moment adaptive moment estimation techniques, you can make use of any of this training and validation method and train your surrogate models. You can give the epochs here, so you can change the epochs, and it's like how many times you want to train and validate your data. More number of epochs will give better fitting, better conversions and all. So based on educated guess, you can select on minimum number of epochs initially required. First, you can start train the model, and in case you have trained the model for some time and now you want to fine tune your model, you can do the changes and continue training. So like that, you have multiple options over here for the surrogate modeling for surrogate modeling and COMSOL interface. So these are different options which are available in COMSOLs, and from here you can find out these options of DNN, PC, GP, and creating design data table. Here you can export. Let's look into the design data table we have created. So you can create the design data tables. It's not required to only like use the surrogate model over here. You want to use the other surrogate functions to train your battery problems. You will have a design data table in the data set, and you can go to let's go to here, and it will take you to the design data table. So here is the design data table created for 5 inputs and 2 outputs, but these outputs are with respect to time. So we have 3 outputs, 5 input, like this you will get the design data table. So that is for today's session for this surrogate model with COMSOL multiphysics. In case you are interested in checking out other options with COMSOL multiphysics, so the other option, which is battery rate capability, which is trained for to get the Regone plot for lithium ion battery, that one surrogate model is also available for this plotting the Regone plot for battery. And in case you want to see how the space dependent problems are handled for the surrogate models, so you can check out one more model, surrogate model, that is for the tubular reactor, which we have created for chemical applications. So here also you can check out different surrogate model techniques or different DNA architecture we have used to train this model. So by visiting all these different models and the digital twin options, which are just showcased in the application library, that those options are also available, those models are available, you make use of that and further train yourself for the surrogate model use with COMSOL multiphysics. With that, I'll conclude this demo and the presentation parts, and just please participate in last poll question. I'll just take a moment. Based on your answers of poll questions, we'll contact you after the webinar and we'll open the session for question and answer. I hope you all like the session, and let's discuss further doubts that you might have for the surrogate models, how to build that in COMSOL, or what option, like the problems you are working on. Yeah.
Thank you so much, Dr. Meenakshi, for the incredibly informative and engaging presentation. I'm sure our audience has taken away many valuable insights. Let's now move to the Q&A session. We have received some thoughtful questions from our participants, so let's dive right in. So, Mr. Sajan is asking, as a vehicle manufacturer, usually we don't have cell level data like their electrodes, separators, etc. In that case, is it possible to simulate the life cycles of the battery PACL using COMSOL?
Yes, it is definitely possible to do that. So in that particular case, you can use the lump model approach and apply the same strategy for giving or drive cycle test or test cycle data. Like with lump model also, you can give the event interface to give your test cycle inputs like C rates and all the segments. And is in the same fashion we just showcased here, just that your model will change from the Newman model to lump model, and you can definitely you can simulate your problem you just mentioned over here without the knowledge of your battery insights. Just with the lump model, you can create the similar architecture for this test cycle or for lump model, and yeah, you can definitely do that with COMSOL. And yes, for further more details, like if you want to check it out, you can contact our team. Yeah, and we'll give you more documents if you want to look into the how to use the lump model and how you can adopt a surrogate model for your particular case. Yeah. Next question, please.
Next question is from Ms. Jyoti. Can we get the actual data to compare with surrogate model data of NMC?
Yes, actually, so once the surrogate model is trained, so you can also check or validate your surrogate model anytime with the actual data. So yeah, it is possible. And to get that, like we don't keep the data with us. So we have trained surrogate models. And for the standard batteries which are already available in market, so we have data for that. So we have trained our model based on the tests data we have gotten in a public domain, and then train the surrogate models. And you can test our surrogate models with the data. If in case you have some data, you can check it out with that one, or we can help you to create one or train the surrogate model with the help of COMSOL multiphysics. Yeah, for that you need to look into our software, and then we yeah.
Okay, I'll move to the next question. Mr. Rohit is asking, how does the accuracy of surrogate models compare to the high fidelity electrochemical models such as P2D, Doyle-Fuller Newman model?
Yeah. So here again, like it will be very accurate. For that thing, what we need is once the DFN model is created, so you need to create the design data table with large number of steps. When you are training it between different C rates, if you take small step size and you create a more data table inputs, with more data table information, you can train your surrogate model very accurately with playing with some DNN architecture. You can get a very accurate surrogate model which can equally train your data similar to DNN model. And the model which we discussed in our session, that is the model we trained on the DFN approach. With Newman model, we have created that model, and when we have trained, so we also have the results. And I think in the animation, you might also observe that we can compute the full DFN model, that particular case, and check the surrogate models, and the model we have created is equally accurate, like similar to the detailed electrochemical model. And yeah, you can take a trial license from, in case you don't have COMSOL, you can take a trial license. You can check out our example. You can see the accuracy over here, and you can also see how instantly it is giving the result, and you can compute the detailed model as well and compare the result on spot. So all these different options for validation of your surrogate models are available in COMSOL multiphysics. You can check out those options, and it is it based on your training inputs. It can definitely be accurate. Yeah. So
Okay. For the last question of the session, Mr. D. Sivkumar is asking, can we use these models to optimize the battery testing cycle to reduce cycle time?
Yes, actually, yes, this is what we are recommending. Like this is one of the like important application of surrogate model when it comes to battery modeling and simulations, that you can test the different test cycles. So once the surrogate model is trained enough, you can actually optimize and get an efficient like test cycle for your battery. So yeah, all these different objectives can be studied with these surrogate models for batteries, and yeah, we do have a lot of materials when it comes to simulating these kind of problem or tackling these problems of batteries in COMSOL multiphysics library and gallery. Yeah.
Okay, I would like to conclude with a heartfelt thank you to our audience for your active participation and thoughtful questions. And a very special thanks to once again Dr. Minakshi for her detailed and enlightening responses. As we conclude today's session, we'd like once again to thank COMSOL for their unwavering support and to all of you for joining us and making this webinar a success. We look forward to welcoming you again soon to another engaging and knowledge-packed session. Thank you so much, everyone. Have a great day ahead.
Please, anyone who ever further want to discuss these things, please contact us. We'll also contact you back based on your poll questions, yeah, responses, so that we can communicate well and we can like make a way out how you can use our software for your research and yeah, designing of your battery pack or battery applications. I hope this session was helpful to you all. Yeah, thank you so
Thank you,
much.
everyone. Thank you.